Kia ora tātou, ko Kate Clark tōku ingoa. Thank you for the introduction. I'm an earthquake geologist at GNS Science, and I focus on the Hikurangi subduction margin. David mentioned this morning that I was here to give the doom and gloom talk, but I actually think Jose just outcompeted me there. So I will just be, here's an outline of my talk. I'm mostly going to start off by talking about how we characterise the modern subduction zone and then look back into the past about how we understand when and where past earthquakes have occurred. Sort of an overview of the whole margin as it's all relevant. The whole margin is, everywhere is relevant to what's happening here, but I will go into a little bit of detail more about what we know about the local area. I'll have a little bit of a focus on the 1947 tsunamis because they're quite an interesting case study, and also talk about past tsunami research as well. So just starting off with characterising the modern Hikurangi subduction zone. So we know about this subduction zone from the seafloor morphology, but also things like deep seismic reflection and little seismic tremors, earthquakes all along the margin, and that's how we delineate where the subduction interface is. So that's that physical boundary between the Australian and the Pacific plate. On that boundary, we characterise how stress is accumulating largely by using both seismicity but also continuous GPS stations. So the continuous GPS is tracking how strain is accumulating or stress is accumulating on that subduction interface. And that sort of colourful purpley yellow black map there is showing which parts of the interface are accumulating more or less stress than other parts of the plate interface. So in general there, where it's sort of red and orange, that's where the subduction interface is accumulating more stress. The purple and black areas are where it's what we call creeping or less strongly locked together. It doesn't mean there's no risk of earthquakes there, it just means that the stress is accumulating at a lower rate. So on that sort of creeping portion of the subduction margin, so that's the area sort of from about Cape Turnagain northwards, the subduction interface is what we call creeping, but there are patches where it's sort of stuck together. And what we also see on this part of the margin is a lot of slow slip events. So slow slip events are often in the media and in the news. They happen up in this part of the world quite often. There's that little GPS graph at the bottom there is showing how GPS stations move in these slow slip events. So slow slip events are these slow earthquakes. They occur over days, weeks, even to years to occur. Up here on the northern part of the Hikurangi subduction zone offshore of Gisborne, they occur about every 2 years or so. So we can have slow slip events. They can be triggered by large earthquakes. The slow slip events themselves can trigger moderate, sort of small to moderate earthquakes as well. But the relationship between slow slip events and really large earthquakes, like what we're talking about here today, the magnitude 9s, that's really poorly understood because we really don't have enough observations of this through time. The good news is that these slow slip events that are occurring, they are about the equivalent of a magnitude of 6 to 7 earthquakes. So they are taking quite a lot of the plate motion, but not all of it. So my work is focused on using the past to understand our future hazard and using past records of earthquakes to forecast future earthquakes. Along the Hikurangi subduction zone, we have had a number of large earthquakes, and someone over there mentioned the 1931 earthquake. These three I've highlighted here. So 1855, Wairarapa was an 8.2. Kaikoura in 2016, and Napier. These were all really large and significant earthquakes, and each of them, except Napier, triggered a reasonably substantial tsunami. But these all occurred on what we call upper plate faults. So these are faults that are going through the Australian plate. On the actual subduction zone itself, we haven't had any really large or great earthquakes during our fairly short historic record. The only really notable ones we've had are actually right up here, just offshore of Gisborne. 1947, there was magnitude 7 and a 7.2 earthquake. And I'll come back and talk about these in a little bit because they did trigger surprisingly large tsunamis for the size of the earthquake. So in general, our historic earthquake record, though it's here in New Zealand, it's quite a rich record, it's generally too short to understand the hazard that these large subduction earthquakes pose to us. So that's why I use the geological record to go back in time and see what has happened. So to understand how these earthquakes, how we preserve a record of these earthquakes in our landscape, there's a little cartoon there of what happens in a subduction earthquake. So you can see part of the land will go up, part of the land will go down, which is the subsidence that we were talking about with the tsunami modelling, and we also get a tsunami. There are other effects as well that can be preserved in our landscape, like landslides and liquefaction, and offshore we have turbidites being deposited in the deep sea. But in general, for the research that I do, I use that uplift, subsidence, and the tsunami deposits to understand these past subduction earthquakes. Here's examples from overseas where they have had really large subduction earthquakes. So along the top there are the photos. There's a forest in Alaska that it's called a ghost forest. It died off when there was subsidence and a magnitude 9.2 earthquake up there. Chile uplift and deposits from the Japan tsunami in 2011. And each of these things can be preserved in our coastal landscape. Here's our Hikurangi subduction margin here, and along here each of these white squares is a site where we've been studying either that coastal uplift, subsidence or tsunami. And these are all just photos of our stunning coastline here, which does preserve all of these features. So we've got these big lagoons down near Wairoa, near Mahia Peninsula, stepped marine terraces out here at Mahia Peninsula and north of Gisborne, lagoons down south, and here's some examples of tsunami deposits as well. So we study all of these features along the margin to try and understand, sort of put things together and try and understand when and where large subduction earthquakes have occurred. I'm going to focus in the next few slides on these three areas, just jump through them all. The southern part of the margin down here, most of my work has actually been over in Marlborough. I'll talk a bit about Hawke's Bay and then what we do and don't know about the northern part of the margin. So down here at Kapara Tahoe, Lake Grasmere, where the saltworks is in Marlborough, we have studied, taken lots of sediment cores from around the margin of that, well, it was a lagoon before they blocked it off and turned it into a lake, so we've taken lots of cores around the lagoon margin. Within these sediment cores, these are examples of what these tsunami deposits look like. So we've seen tsunamis have come in and picked up lots of shells, little rocks and mollusks and microfossils from upshore and dumped them over in this lagoon. And we can do analysis on these, looking at the fossils, radiocarbon dating these shells to get really accurate timing of these tsunamis, and tracing out how far inland that tsunami went. We combined this geology study with tsunami modelling to try and understand what type of earthquake could have deposited these tsunami deposits. And we really end up seeing that it's really only the subduction zone that could produce a tsunami large enough to transport these shells and other things as far inland as they were found. So we also looked at the other nearby, like the Marlborough area in Wellington. It's riddled with these upper plate faults as well, so we also tested some of those, like the Awatiri fault, the Wairoa fault. None of these were really large enough. They couldn't produce a large enough earthquake or the right type of seafloor movement to produce such a large tsunami. We put that all together, and this is sort of the critical record. We combined the Lake Grasmere ages with some previous work that I had done closer to Blenheim and the Wairoa lagoons, and we end up saying this fairly, like, for geological timescales, it's fairly clockwork, a large earthquake about every 500 years. And we can use that, this is just showing you that distribution on the recurrence interval, so about 500 years, plus or minus, I can't remember what it is, about 100 years is the recurrence interval there. These earthquakes were probably about magnitude 8.5. Some might have been smaller, some might have been larger. We can't quite get precision on the size of them from this type of research. But what is really interesting is that quite remarkable regularity of these large subduction earthquakes on the southern part of the margin.
So I'll skip now to the central part of the margin. This is 2 photos of Ahuriri Lagoon near Napier. Most people are probably familiar with it, where we now have the airport along here. So this area went up about 1.5 metres in 1931, which is, as I mentioned, that was an earthquake on one of the upper plate faults, so not the subduction zone. If we take sediment cores throughout Ahuriri Lagoon, we actually see this remarkable record of the land repeatedly dropping down. So this is one of my students, Charlotte, looking at these cores, and each of these soil layers represents a previous land surface, and then the grey silts represent where the soil, the land surface dropped down, and then it was inundated by the intertidal lagoon again. So we can go through and date the timing and measure the amount of subsidence that occurred in each of these earthquakes. So I just wanted to point out that contrast between going up in 1931, but the geological record shows that the long-term signal is of this area dropping down, probably in large subduction earthquakes, but we do have some upper plate faults in this area that are also capable of causing that subsidence as well. So there's actually several sites in Hawke's Bay that we've studied. There's some records up here in the Te Paeroa Lagoon near Wairoa, site north of Napier, Pakuratahi, and Ahuriri Lagoon. If we put together all these earthquake records, and they're sort of represented different levels of certainty, some earthquakes we really have high confidence that they occurred, some of them they're a bit fuzzier, so we have different levels of confidence for each earthquake. But if we put this all together, we end up with probably a recurrence interval somewhere between 1,200 to 2,300 years. It's the subduction. So I think the key thing about this is that your recurrence interval, so the timing between these large subduction earthquakes, is quite vastly different from the southern part of the margin around Wellington to Hawke's Bay. Much longer recurrence interval in Hawke's Bay, but there's still, that's still fairly frequent for really large earthquakes. And then if we skip further to the north of the margin to where we are here, one of the key sites we've looked at up here was a study recently done by Nicola Litchfield at the Pākarai River mouth, which is just north of the settlement of Whangarā, and Puatai Beach a little bit further north. So Nicola looked at these marine terraces going down to the sea here and here at Puatai Beach. She excavated these long trenches across the terraces, and in these trenches she was able to look at those the deposits from the former beaches when each of those steps was at the beach level, takes the shells out to radiocarbon date them, measures how high those shells are now, uses other constraints like the ages of tephras, like there's a photo of the Taupo tephra there 1,800 years ago. And this helps us understand both the amount of uplift that occurred and the timing of when that occurred. So what was interesting about these sites is they're actually very close together, but they almost have completely offset timings of earthquakes. So we could see from this, if you had the subduction earthquake causing this uplift, you should have the same earthquake timing at both sites, but they were actually offset in time. So we went to our colleagues at NIWA and asked them to re-look offshore, and basically it's a big mess out there of upper plate faults. Lots of complexity happening, and what we think is that each of these beaches is responding to earthquakes on different fault lines offshore. So we're not getting a subduction earthquake record from this site, we're getting a record of earthquakes on these offshore faults. They're probably smaller earthquakes than the subduction zone. Not quite sure what the precise magnitude would be, but it's still concerning that, and on average you're getting 5 earthquakes here over 2,000 years, so that's a frequency of about 400 years for these offshore earthquakes that have caused substantial uplift of the coastline north of Gisborne. I'm just going to focus now on the 1947 tsunamis, because I'm not sure how familiar people will be with these historic events, but they occurred just offshore, one Yeah, the first one here, March, and then one in May of the same year. These were reasonably large earthquakes. They're about magnitude, the first one was about magnitude 7 to 7.1, 6.9 to 7. But what was interesting is that they have a local magnitude of only about 5.6 to 5.9. So they were large earthquakes in terms of the amount of slip that occurred, but not large earthquakes in terms of how they were felt and the sort of strong shaking that they produced. They really only produced quite a long, slow rolling motion, so really slow, call it a slow rupture velocity. The earthquake occurred quite slowly over sort of minutes rather than intense shaking over seconds. The March tsunami produced really quite significant tsunami heights of up to 10 metres along this part of the coastline. The May tsunami was up to 6 metres, concentrated a bit further north. Here's just some photos and some of the historic accounts of what occurred. So both of these are what we call tsunami earthquakes. They're a particular sort of category of earthquakes that are really characterised by producing large tsunamis for the relatively moderate size of earthquakes that they are. They usually take place on the really shallow parts of the subduction interface, so quite far offshore. And they're characterised by occurring quite slowly, radiating energy at these lower frequencies, and they're usually only weakly felt, which is really concerning for how people might self-evacuate in response to such an event. You can see, just have a look at some of the photos there. Terapuri Hotel, this one was from Wainui Beach, just close to us here. Here's some more of the historic photos here. There were, I believe, no fatalities from these events. This cottage here, I think it's the Hall Cottage. This was up at Puawa. There were some people caught in that cottage, and quite remarkable account of how they were tossed around like being in a agitator washing machine, but they did manage to survive, were swept a ways inland. This also took out the bridge over the Puawa River and transported that some distance inland. Down here at Mahanga, near Mahia Peninsula, it wasn't the tsunami wasn't as high, but it was notable, lots of historic accounts of how far it went inland, transporting fish and stingrays and so on, quite far inland down there. So this brings me to the historic records that we have of tsunamis, and at GNS we have a historic tsunami database that sort of accumulates and archives all these historic accounts of tsunamis around the New Zealand coast. And you can see there the types of records that are held within this tsunami database. So we go from some Māori oral histories to written records from sort of the 1830s onwards, diaries, letters, and then throughout the sort of from about the 1960s onwards, we start getting instrumental records, tide gauges, more recently dart buoys, and then a massive cascade of social media accounts of tsunamis as well. So this is all, we try to archive this all within the database. Sorry, this is just a snapshot of the New Zealand Historic Tsunami Database. It was recently upgraded thanks to funding from EQC to get it into a much more user-friendly digital format. But what I've highlighted here is, up here in the Tairāwhiti region, quite a high density of observations in the historic times. Most of these observations, though, are from those 1947 tsunamis, and quite a number from the 1960 Chile tsunami as well. So most of the historic observations are from those two. I did trawl through and try and find if there were other interesting tsunami observations from this region. 1840 seems to have been a reasonable local source earthquake, probably. There's an account there of fish being washed in, I think it is up at Te Araroa, and a boat being stranded all the way up at Whirianga. So, but 1840, it's really hard to tell where that earthquake might have occurred or what type of earthquake it was. 1877, there's a record in there of a strange occurrence out at sea that was observed by ships. They suspected it might have been a sort of hydrate gas emission from the seafloor or potentially a submarine landslide. Seems to have just been a large disturbance at sea. There isn't any accounts of an actual tsunami produced by this, but it did occur on a fairly sparsely populated part of the coastline, in 1877 as well. This brings me to the paleo-tsunami. So paleo-tsunami is simply tsunamis that occurred prior to our written and instrumental records. They're commonly identified around our coastline in the geological record by something anomalous in the coastal deposits. So there's a little figure here showing how tsunamis pick up debris from offshore. I guess in today's world it would be the logs from the port, deposit them inland where they're then preserved, and if we're fortunate enough to take a sediment core in the right place, we might capture them. There's examples there from Chile where they have a really, really consistent and long record of paleo-tsunamis as well. So similar to the historic tsunami database, NIWA hold a paleo-tsunami database that's really interesting to have a look through. And this simply compiles all the locations around New Zealand where paleo-tsunami studies have been undertaken or something unusual has been noticed in the coastal sediments that might be indicative of tsunamis. But as you can see, I'll go back to that, there's not a lot in the database from the northern part of the margin. It's quite a notable contrast between the historic database, the density of points that we have along the Tairāwhiti coast, versus the paleo-tsunami database. So we really have very few paleo-tsunami records from this northern part of the margin. I suspect this is mostly for lack of intensely looking for them rather than a lack of actual occurrence. Sorry, I'll just go back to that. So I'm just going to focus now on two areas where we have been undertaking work to try and fill in some of these gaps and try and see if there are paleo-tsunami deposits. So the first one here is that Puatai site that I showed the marine terrace trenches of, done by Nicola Litchfield. And at this site, there's some really subtle little sand layers. So this is an old beach that was uplifted by an earthquake. It then was stranded up high, probably had some hill slope debris deposited on it, what we call colluvium. And then up in the top soil layers are these really skinny little sand layers. You can see them here. They potentially could be a record of past tsunamis, tsunamis that have come in, picked up sand from the beach and transported it high onto these marine terraces. Really hard to characterise and study these types of deposits. They're difficult to accurately date. If they are tsunami deposits, we were able to understand the age of them by looking at what terraces they sat on. So there's possible evidence at this site for 3 large tsunamis in the last 1,200 years. So one of them reaching up to 12 metres above sea level, another 9.5 metres above sea level. And this information is in a report done for EQC by Nicola Litchfield. So this is a site it would be really nice to try and verify these records, see if they are correct, because it would be really useful to have more tsunami records along this part of the coastline. Where we are starting to make good progress on looking at paleo-tsunami deposits is in Hawke's Bay. There has been previous work done, as I mentioned, near Wairoa and the large lagoons there that had found evidence of tsunamis, but we'd never found anything closer to Napier. But we have 2 studies in progress. One at, these are those Ahuriri cores that I showed earlier. So as well as having this record of the ground dropping down in large subduction earthquakes or upper plate fault earthquakes, some of them are associated with these tsunami deposits. So we've had the ground drop down suddenly, and at the same time, immediately afterwards, a tsunami come in and deposit this, this sort of chaotic, mixed-up unit of sediment, and then it sort of returns to a fairly quiescent lagoon environment again. Probably a similar age deposit, a little bit, hang on, I think I've actually got this one wrong. These ones are from Ahuriri, which is further south. These are from Pakuratahi, which is the site further north. These are Charlotte's cores. seeing these chaotic tsunami deposits at this site here. So we're trying to radiocarbon date these, see if they're the same event, and try and link it back to what caused that tsunami, which is most likely a large subduction earthquake. So it's really nice to finally be starting to see evidence near Napier to verify that these large subduction earthquakes most likely are associated with large tsunamis as well. So just to sort of wrap up of where we are at in a sort of broad sense of understanding the recurrence of subduction earthquakes and tsunamis along the Hikurangi subduction zone. When we put together all the sort of sites that I've mentioned, and I've only sort of done a flyover of several of them here, but the last sort of time we see a really large rupture affecting most of the margin was about 850 years ago. Down in the southern part of the margin, we see that this was definitely associated with a reasonably large tsunami. It probably ruptured the southern part of the margin, so underneath Wellington, most likely ruptured underneath Hawke's Bay. We haven't yet found any evidence that it ruptured as far north as we are here. So it's a bit uncertain if it's propagated all the way through. A summary here of the recurrence statistics as we move along the margin. So Wellington area, about 500 years, unfortunately, where I live. Hawke's Bay looks like the recurrence intervals get substantially longer, larger gaps in between these large earthquakes. And then on the northern part of the margin, we unfortunately really have very little constraint on the recurrence of these really large subduction earthquakes. Paleo tsunamis, similar. We have really strong evidence in the south that subduction earthquakes are associated with large tsunamis. Hawke's Bay, we've got emerging evidence that they are. But up here on the northern part of the margin, there's no strong evidence for really large paleo tsunami having occurred, but this is probably because we've had very few targeted in-depth studies for paleo tsunami on this northern part of the margin. So to me, there's still, this is a lot of progress from about 10, 20 years ago when we sort of started studying this, but there's still a real question around how often does the central part of the margin rupture with the southern part of the margin, and also questioning about whether this northern part of the margin, can it even host really large earthquakes, and how far north can ruptures propagate onto the Kermadec Trench, because we name them different things, but there's no physical barrier between the Hikurangi subduction zone and the Kermadec Trench. It's a continuous subduction zone. So it would be really good to know how large can earthquakes get along this part of the margin. And of course, the further north you rupture the subduction zone, that has greater implications for the tsunami that can get around and into the Bay of Plenty, Coromandel Peninsula, and affecting Auckland as well. And of course, you can have it the other way. Could we have earthquakes propagating from the Kermadec Trench coming southward and triggering off large ruptures underneath the northern part of the Hikurangi subduction zone? So I believe that is it for me today. Thank you very much.